Somewhere above the teapot-shaped pattern of stars in the constellation Sagittarius, drifting in a part of the sky so thick with starlight that it looks almost like a wound in the dark, there is a star that is drawing, not painting, not exploding, not simply burning the way most stars burn, drawing. Slowly, patiently, in a perfect and repeating curve, a dying star 8,000 light-years from where you are lying right now is tracing the same spiral shape over and over again, the way a child traces a spiral on paper without ever lifting the pencil, except this pencil is made of carbon dust and starlight, and the paper is the empty vacuum of space itself, and the spiral has been drawing itself, unbroken, for longer than human beings have had a written language. Tonight, that is where we are going. Not into anything frightening, not into anything you need to brace yourself for, just into a quiet corner of the galaxy where a star called WR104 has spent its final chapter doing something almost nobody expected a star to do. It has been spinning a pattern into existence, coil after identical coil, a structure so geometrically perfect that when astronomers first saw it, they assumed for a moment that they were looking at a mistake in their equipment, rather than a feature of the universe. Let your shoulders drop. Let your breathing slow down to match the pace of this voice. There is nowhere else you need to be right now except here, with me, looking out toward Sagittarius, toward a star drawing its last and most beautiful sentence onto the dark. Before we go any further, I want to ask you something small. Wherever you are listening to this from, whatever city or country, whatever time it is on your clock right now, drop it in the comments. I love seeing where in the world this finds people, what time zone, what kind of night it is for you, and if stories like this one help you unwind, help you drift off, consider subscribing so the next one finds you too. Now, let's go back to the spiral. Stars, for the most part, do not draw things. A star is usually just a star, a glowing sphere of plasma, fusing hydrogen into helium in its core, radiating light outward in every direction, with a kind of stubborn, symmetrical indifference. The sun does not draw anything. It simply burns, evenly, in a pattern that has no particular shape beyond round. Most of the 200 billion or so stars in the Milky Way are exactly that, unremarkable in their geometry. They are spheres of fire, hanging in the dark, doing the same predictable thing for billions of years. WR104 is not most stars. WR104 belongs to a tiny, exotic, almost theatrical category of stars, known as Wolf-Rayet stars, and it is paired with a stellar companion in a way that turns the two of them together into something closer to a cosmic lighthouse with a spinning beam, except the beam is not light. It is dust, solid, physical, carbon-rich dust, the same basic kind of material that makes up soot from a candle flame, except formed under conditions so violent, so blisteringly hot, and so seemingly impossible that for decades astronomers were not sure how dust could form there at all. And because that dust gets carried outward by ferocious stellar winds while the two stars orbit each other, the dust does not spread out evenly into a uniform cloud. It gets flung outward along a single moving point, the way water flies off the end of a rotating lawn sprinkler, except instead of water droplets falling onto grass, you get solid particles of stardust spreading out into the vacuum of space in a long, continuous, perfectly logarithmic curve. A spiral, coil after coil after coil, frozen in place by the immense distances and immense timescales involved, so that when you look at it through a powerful enough telescope, what you see is not a blur, not a smudge, not a shapeless cloud. You see a pinwheel, an actual, recognizable pinwheel, glowing softly in the infrared, more than 200 astronomical units across, which is more than 6 times the distance from the Sun to Pluto, sitting quietly in the dark, slowly turning. This is the story of that star. Where it came from, how astronomers found it, why it terrified the public for a few strange years in the early 2000s, why a more recent study has quietly walked that fear back, and what this single, lonely dying star can teach us about the deep machinery of how the universe builds, sheds, and recycles itself. We are going to take our time with it tonight. There is no need to rush. The star certainly is not rushing. It has been drawing this same spiral, patiently, coil by coil, for longer than recorded human history, and it will likely keep drawing it for a very long time yet. So settle in, get comfortable, let the weight of the day fall away from you, and let's go meet the star they once called, only half-jokingly, the Death Star. Let's begin, gently, with the basic question. What exactly is a Wolf-Rayet star, and why does it behave so differently from every other star you have ever heard of? To understand a Wolf-Rayet star, you first have to understand that not all stars are created equal, not even close. The Sun, our familiar, life-giving, perfectly ordinary star, has a mass that astronomers use as a kind of yardstick for the rest of the universe, one solar mass. It is comfortable, it is stable, and at its current rate of fuel consumption, it will burn steadily for somewhere around 10 billion years before it finally runs out of hydrogen in its core. The Sun is, in cosmic terms, an unhurried star. It takes its time. A Wolf-Rayet star is the opposite of unhurried. These are some of the most massive stars known to exist, typically beginning their lives with at least 20 times the mass of the Sun, and in some documented cases, considerably more than that. Some of the most extreme examples in catalogs of these stars carry well over 100 solar masses, sometimes closer to 200. And here is the thing about very massive stars that almost feels unfair when you first learn it. The more massive a star is, the faster it burns through its fuel, not the slower. You might intuitively assume that a star with 20 or 50 times more hydrogen to burn would last 20 or 50 times longer. It is exactly the opposite. The increased mass dramatically increases the internal pressure and temperature in the star's core, which dramatically accelerates the rate of nuclear fusion, which means these enormous stars burn through their fuel reserves far faster than small, modest stars like our Sun. A star 20 times the mass of the Sun does not live 20 times longer. It often lives only a few million years, a flicker compared to the 10 billion years the Sun gets to enjoy. Wolf-Rayet stars represent the final, most dramatic chapter in the life of these massive giants, the stage that comes right before they detonate as supernovae. By the time a star earns the Wolf-Rayet designation, it has already burned through the easy stages of its life. It has fused hydrogen into helium for as long as it reasonably could. As that fuel ran low, the star underwent a series of dramatic internal transformations, expanding, contracting, sometimes passing through phases as a red supergiant, or what astronomers call a luminous blue variable, a star so unstable that it periodically throws off enormous eruptions of mass in episodes that can shed more material in a single outburst than entire smaller stars contain in total. Through all of that, the star is losing mass continuously, peeling away its own outer layers like a fruit losing its skin, driven by radiation pressure so intense that the star is, in a very real and literal sense, blowing itself apart from the inside out. Wolf-Rayet stars are so bright, so luminous, that the pressure of their own light is enough to drive a constant, ferocious stellar wind off their surface, a wind that can travel at speeds of 1 to 2,000 kilometers per second, fast enough to cross the distance from the Earth to the Moon in a matter of minutes. This wind carries away an enormous amount of mass. Wolf-Rayet stars typically lose somewhere between half and 90% of their original mass over the course of their lifetimes, much of it shed in this final, dramatic stage. Researchers have noted that a Wolf-Rayet star can shed half its initial mass in less than 100,000 years, an almost unthinkably brief window measured against the age of the universe. By the time the mass loss has stripped away the star's outer hydrogen envelope entirely, what is left exposed is the hot, helium-rich, sometimes carbon-rich, or even oxygen-rich core of the star, glowing at the surface with extraordinary heat, often tens of thousands of degrees, hotter than almost any other class of star known. This exposed inner material is what gives Wolf-Rayet stars their unusual identifying feature, which is how they were discovered in the first place. Back in 1867, two French astronomers named Charles Wolf and Georges Rayet, observing through a telescope at the Paris Observatory, noticed a handful of stars in the constellation Cygnus with strange, broad emission lines in their spectra. lines that did not match the absorption line patterns astronomers were used to seeing in ordinary stars. Those broad emission features were the signature of a star surrounded by a dense, fast-moving stellar wind, the chemical fingerprint of an object that was visibly, spectroscopically, in the process of flying apart. That class of stars now carries their names. A Wolf-Rayet star, abbreviated simply WR, followed by a catalog number assigned according to the order in which these stars appear when you scan across the sky by right ascension, the astronomical equivalent of longitude. WR104 simply means it was the 104th Wolf-Rayet star cataloged in that particular numbering scheme. A scheme that, even though the original catalog has been updated and expanded many times since, the Milky Way's Wolf-Rayet stars are still numbered today. Astronomers further divide Wolf-Rayet stars into subtypes based on which elements dominate their spectra. There are nitrogen-rich WN stars, where the products of incomplete hydrogen fusion via something called the CNO cycle are visible at the surface. There are carbon-rich WC stars, where helium fusion byproducts, carbon and oxygen, have been exposed. And there is a rarer, even more extreme category called WO stars, oxygen-rich stars, representing what may be the very last gasp before a massive star's core finally collapses. WR104 itself is classified as a WC star, meaning the dust-forming, carbon-rich wind streaming off its surface is rich in exactly the raw material needed to manufacture solid dust grains, which, as we will see in a moment, turns out to matter enormously for the spiral shape that made this star famous. It is worth pausing here, in this quiet, comfortable moment, to really sit with what a Wolf-Rayet star represents. It is not simply an old star, it is a star in its terminal stage, a star whose outer layers have already mostly been stripped away, a star burning through its remaining fuel at a blistering pace, a star that we know, with near certainty, is going to end its life as a supernova. The only real question is not whether, but when, and on cosmic timescales, when is a word that can comfortably mean anything from tomorrow to several 100,000 years from now, and to the universe. Both of those answers are essentially the same thing: soon. But here is what makes WR104 different from the countless other Wolf-Rayet stars scattered across the Milky Way. It is not alone. It has a companion. And that companion changes everything about how this star's final years are going to look from the outside. Wolf-Rayet stars on their own are simply too hostile an environment for solid matter to form near them. The radiation pressure pouring off a star, burning that hot, that bright, should in theory blast apart any dust grains attempting to condense out of the stellar wind before they ever have the chance to grow. For a long time, this was one of the genuine puzzles of Wolf-Rayet astrophysics. Astronomers kept detecting infrared emission from these stars, the unmistakable signature of warm dust glowing nearby, and yet the physics of the situation seemed to forbid dust from forming there at all. It was, for years, a contradiction sitting quietly in the data, waiting for someone to explain it. The answer, it turned out, involves a second star. WR104 is part of a multiple star system, with a Wolf-Rayet component and at least one, possibly two, additional companion stars, hot, massive, main sequence stars of what astronomers classify as type O or B, often shortened simply to OB stars. These companions also produce their own powerful stellar winds, though typically less extreme than the Wolf-Rayet star's wind. And where the wind from the Wolf-Rayet star slams into the wind from its companion star, something remarkable happens. The two streams of high-speed material crash into each other, and at that violent boundary, that shock front, the material gets compressed enormously, squeezed into a dense, narrow region where temperatures, although still very hot, are dramatically lower than out in the open wind, and pressure is dramatically higher. It is in this narrow, fleeting cocoon, this place that one researcher memorably described as feeling, from the dust's point of view, like being caught between the frying pan and the fire, that conditions finally become survivable enough for solid dust grains to nucleate and begin to grow before the radiation can tear them apart again. This is the essential secret behind every pinwheel nebula ever discovered. including the one circling WR104. It is not a single star doing something strange on its own. It is two stars locked in mutual orbit, their winds colliding violently along a shared boundary, manufacturing dust at the only place in the entire system where dust has any chance of surviving. And because that collision zone is not standing still, because it is being dragged around the sky by the orbital motion of the two stars circling one another, the dust being produced there does not simply puff outward into a featureless shell. It gets swept into a spiral. I want you to actually picture this for a moment, slowly, the way you might picture something just before falling asleep. Picture a rotating sprinkler head on a summer lawn, water jetting outward in a continuous stream, while the sprinkler itself turns in a slow circle. From above, the water does not form a straight line outward from the sprinkler. Because the source is rotating while the water keeps moving outward at a steady speed, the path traced by any given droplet curves, and the cumulative pattern, frozen for a fraction of a second in a photograph, would look exactly like a spiral, water curling outward from the center in smooth, even coils. That is precisely the mechanism at work around WR104, except the rotating source is not a garden sprinkler. It is a binary star system. The water is not water. It is microscopic dust grains, each one essentially carbon soot, formed in the wind collision zone and then carried outward at enormous speed by the pressure of the stellar winds behind them. And the slow, steady rotation of the sprinkler head is the orbital motion of the two stars, swinging around their common center of mass once every 220 days or so, dragging the active dust-forming region around with them in a circle, coil after identical coil, for as long as the system keeps producing dust. This was first directly observed in 1998, and the story of that discovery is itself worth slowing down for, because it is a genuinely lovely piece of scientific detective work, the kind of careful, patient observation that this channel particularly loves to dwell on. Take a breath here with me. We are about halfway through getting properly oriented, and there is no rush at all to where we are going next. In April of 1998, a team of astronomers working at the Keck Observatory in Hawaii, home to the largest optical telescopes on Earth at that time, turned their instruments toward this faint, obscure star in Sagittarius. The team was led by Peter Tuthill, working alongside colleagues John Monnier and William Danchi, and they were using a clever and somewhat unconventional imaging technique called aperture masking interferometry. Rather than using the full light-gathering surface of the enormous Keck telescope mirror, the technique involves physically masking off most of that surface, leaving only a handful of small openings, which then function collectively like a miniature array of smaller telescopes working together. By carefully analyzing the way light waves passing through these separate openings interfere with one another, the team was able to reconstruct an image with far greater clarity and resolution than a conventional photograph could achieve, a technique far less sensitive to the blurring and shimmering effects of looking through Earth's turbulent atmosphere. This mattered enormously, because the apparent size of whatever structure surrounded WR104, as seen from Earth, was almost impossibly small. The star sits roughly 8,000 light-years away, and the spiral structure around it, while genuinely enormous in absolute terms, more than 200 astronomical units across, subtends an angle in our sky so tiny that researchers later compared the achievement to resolving fine details on the head of a pin from a distance of 2 miles. Without the careful, deliberate technique of interferometric imaging, all astronomers would have seen was a fuzzy, featureless blob of infrared light, indistinguishable from any number of other faint, dusty stars. But with this technique, in that April 1998 observation, and then in follow-up observations in June and September of that same year, the team captured something nobody had ever clearly seen before: a spiral. An honest-to-goodness, unmistakable spiral structure, visible in the infrared, wound around the star in a clean, mathematically regular pattern. When they compared the 3 separate epochs of observation, April, June, and September, they could see the spiral pattern had visibly rotated between each image, the same structure simply having turned in place over the intervening months, exactly as you would expect if a rotating source deep inside the spiral was continuously laying down new material, while the old material drifted slowly outward, unchanged in shape, carried along like a conveyor belt. The team published their results the following year, in April of 1999, in a letter to the prestigious journal Nature, and the title alone tells you how they understood what they had found: a dusty pinwheel nebula around the massive star WR-104. It was, as they described it, the first of an entirely new class of nebula, never directly imaged before. Not simply a curiosity, not simply a strange-looking object, but the prototype for a whole category of objects that astronomers would go on to find, slowly, scattered elsewhere across the galaxy, once they finally knew what to look for and how to look for it. From those careful images, the team was able to do something remarkable. Without ever directly resolving the two individual stars at the center of the system, stars too close together and too far away to separate even with the most powerful telescope available, they were able to deduce an enormous amount about the system simply by studying the geometry of the dust trail it had left behind. The spiral itself became a kind of fossil record, a physical, persistent imprint of the orbital motion of two stars that themselves remained invisible, hidden inside the glare of the dust they had created. By carefully measuring how tightly wound the spiral was and how fast it appeared to be rotating between observations, the team calculated an orbital period for the inner binary, an estimate of around 220 days, with a margin of uncertainty of about 30 days in either direction. Later, more refined observations over the following decades using more advanced instruments would narrow this figure down considerably, with various studies converging on values in the range of 240 to 242 days, with one careful, long baseline study using data collected over more than 2 decades, arriving at a period of 241.5 days, plus or minus half a day. 2/3 of an Earth year, give or take, for the two central stars to complete one full circuit around their shared center of mass, dragging the dust-forming wind collision zone around with them the entire time. The team was also able to determine something else from the shape of the spiral, something with implications that would later make this otherwise obscure binary star system into an unlikely subject of tabloid headlines and breathless cable news segments. Because the spiral appeared from Earth's perspective as a clean, nearly circular pattern, rather than as a tightly compressed, oval, or foreshortened shape, the geometry strongly suggested that astronomers on Earth were viewing the system almost directly along its rotational axis. In other words, we were not looking at this spinning system edge-on, the way you might view a vinyl record from the side, where the grooves would appear as a flat, compressed line. We were looking down nearly straight at the top of it, pole-on, the way you might look directly down at a spinning record from directly above, watching the grooves trace their full, perfectly circular path. This single observation, this quiet, almost technical detail about viewing geometry, would turn out to be the thread that, years later, an entirely different group of researchers would pull on, and it is the thread that eventually led some corners of the press to give this distant, otherwise unremarkable dying star its unforgettable, slightly dramatic nickname. Let's slow down again here, breathe, and gently turn toward that part of the story. If you simply step back and look at an image of the spiral around WR-104, what you are seeing is one of the cleanest natural examples in the known universe of something mathematicians call an Archimedean spiral, sometimes also referred to as a linear spiral. This is a very specific, very particular kind of curve, named after the ancient Greek mathematician Archimedes, who described it more than 2,000 years ago. The defining feature of an Archimedean spiral is that, unlike many other kinds of spirals you might be familiar with, such as the logarithmic spiral found in the shell of a nautilus, or in many spiral galaxies, an Archimedean spiral maintains a constant distance between each successive coil, or winding, as you move outward from the center. The gap between one loop and the next loop right outside it stays the same all the way out, rather than growing or shrinking as you move further from the middle. This is exactly what you would expect from the lawn sprinkler analogy we talked about earlier, and it is precisely what the careful mathematical analysis of the 1998 Keck images revealed. The dust streaming away from WR-104 moves outward at what is, for all practical purposes, a roughly constant velocity, somewhere in the range of 1 to 2,000 kilometers per second, depending on the specific study and the specific location measured within the spiral, while the source at the center rotates at a steady, predictable rate. Constant outward speed, combined with constant rotational speed, mathematically produces exactly this kind of evenly spaced, linear spiral. It is not a coincidence, and it is not an artistic flourish of nature. It is the direct, almost textbook geometric signature of two simple physical processes happening simultaneously, recorded and preserved in solid matter, the same way the regular, repeating rings inside a tree trunk preserve a quiet record of each passing year. By measuring the spacing between the spiral's coils, and combining that measurement with the orbital period derived from how the structure rotated between observations, researchers were able to estimate the velocity of the dust-bearing wind, finding it to be moving at roughly translates into something on the order of several million kilometers per hour, an almost unimaginable speed by any earthbound standard, fast enough that the dust crosses the entire distance from the sun to the earth in a matter of hours, rather than the 8 minutes it takes light to make that same trip, but still vastly slower than light itself. The overall scale of the structure, once properly measured, turned out to be genuinely enormous. The visible spiral nebula spans more than 200 astronomical units in diameter, more than 6 times the average distance between the Sun and Pluto. Later, deeper observations using more modern and more sensitive instruments at the Very Large Telescope in Chile, conducted using both near-infrared and mid-infrared cameras called Sphere and Visier, managed to trace the spiral structure out even further, detecting as many as 5 full revolutions, 5 complete coils, of the spiral pattern, extending the visible dust structure outward to nearly 2 arcseconds from the central stars, as observed from Earth, corresponding to a span representing roughly the past 20 years of the system's accumulated dust production at the time of that particular study. Every coil you can see in those images is a kind of frozen photograph of one previous orbital cycle, layered one after another, outward in time, like the growth rings of a tree, except instead of being laid down once a year, each ring represents roughly 240 days of the system's history. I want you to sit with that image for a moment, because there is something genuinely beautiful and almost meditative about it. The kind of idea this whole channel exists to slow down and dwell inside of. Every single loop of that spiral is a snapshot of a particular moment, a moment when 2 ancient stars, locked in their mutual gravitational dance, briefly created the right conditions for solid matter to condense out of nothing, out of pure superheated gas, into actual grains of carbon dust, no bigger, in the inner parts of the spiral, than about 100 angstroms across, smaller than most viruses, smaller than most things we could meaningfully picture without a microscope. And that dust did not simply vanish or scatter randomly. It held together, drifting outward, carried by the relentless pressure of the wind behind it, preserving the exact shape of the moment it was born, for years, for decades, slowly fading and dispersing, only after it has traveled enormous distances from the stars that made it. Researchers have estimated, based on detailed radiative transfer modeling of how the dust absorbs and re-emits starlight, that the WR-104 system manufactures new dust at a rate of roughly 8 times 10 to the negative 7th solar masses per year. An admittedly small number on its own, but one that, multiplied across hundreds of thousands of years, represents a meaningful contribution to the raw material drifting through that region of the galaxy. That dust corresponds to approximately 2% of the total carbon being produced and ejected by the Wolf-Rayet star's nuclear processes and stellar wind, carbon forged deep inside the star through the fusion of helium, carbon that is now, slowly, patiently, finding its way back out into interstellar space, where it will eventually mix into the vast clouds of gas and dust that one day, given enough time, collapse to form entirely new stars, and quite possibly, entirely new planets. But it is that very same geometry, that clean, pole-on view of the spiral that made it so beautifully photographable in the first place, that also gave WR104 its uneasy reputation. The reputation that, for a strange handful of years in the middle of the 2000s, made this obscure star in a part of the sky most people have never bothered to look at into something approaching a minor cultural phenomenon. Take a slow breath here, and let's gently walk through that part of the story together. There is nothing here to be anxious about. I promise you that by the time we get to the end of this section, the picture will be considerably calmer than where it begins. Wolf-Rayet stars, as we have already discussed, are destined to end their lives as supernovae, the catastrophic, brilliant explosion that marks the death of a massive star, when its core can no longer generate enough outward pressure to resist the relentless inward pull of its own gravity. For most stars, even most massive stars, a supernova, while extraordinarily violent, releases its energy in a relatively even, all-directions pattern, like a flashbulb going off. Brilliant but undirected. But some massive stars, particularly ones that are spinning extremely rapidly at the moment of their collapse, are theorized to produce something far more concentrated and far more energetic, an event called a long-duration gamma-ray burst. Rather than radiating energy outward evenly in every direction, the collapsing core of a sufficiently fast-spinning star can, under the right conditions, launch a pair of narrow, tightly focused jets of extremely high-energy radiation and particles, blasting outward along the star's rotational axis in two opposite directions, like a cosmic lighthouse beam, rather than spreading evenly like a street lamp. These jets are thought to be associated with the formation of a black hole at the dying star's core, with infalling material spiraling down and launching relativistic jets along the path of least resistance, straight along the axis of rotation, out through the poles of the star. Gamma-ray bursts are, without exaggeration, among the most energetic events known to occur anywhere in the observable universe. A single gamma-ray burst can release, in the span of just a few seconds to a few minutes, roughly as much total energy as the sun will radiate over its entire 10 billion-year lifetime, all of it concentrated into two narrow, focused beams. Because of this extreme directionality, the danger posed by a gamma-ray burst depends enormously on geometry. If the beam happens to be aimed precisely at you, even from extraordinary distances, the effects could be devastating. If the beam is aimed even slightly away from you, in almost any other direction at all, the event might pass entirely unnoticed, its tremendous energy spent harmlessly into empty space, millions or billions of light-years from where anyone could ever observe it. Researchers studying the potential effects of a sufficiently close gamma-ray burst striking Earth's atmosphere have modeled scenarios involving the depletion of the planet's protective ozone layer. According to several published atmospheric studies, a gamma-ray burst occurring within roughly a few thousand parsecs of Earth could, within a matter of minutes, trigger chemical reactions in the upper atmosphere involving oxygen and nitrogen molecules, generating nitrogen oxide compounds that aggressively destroy stratospheric ozone. Modeling work published by researchers including Brian Thomas and colleagues has estimated that a typical nearby burst could produce globally averaged ozone depletion of up to roughly 35 to 38%, with localized depletion in certain regions reaching considerably higher, with recovery to normal ozone levels potentially taking several years afterward. With diminished ozone protection, increased ultraviolet radiation from the sun reaching the surface could pose serious risks to surface-dwelling life, particularly the microscopic plankton that form the foundation of marine food chains, though deeper ocean life would likely remain shielded by the simple physical protection of water itself. It is worth being honest and clear here, in the gentle, factual way this channel always tries to be. These are genuinely serious potential effects, documented in careful peer-reviewed scientific literature. But they require an extraordinarily specific and extraordinarily rare set of conditions to actually occur. A nearby massive star, spinning unusually fast, ending its life in precisely the right way, with its rotational axis happening to point with remarkable precision directly at our solar system. This is, to be clear, not remotely a common or routine astronomical event. It has likely never happened to Earth in the entire history of complex life. Though some researchers have speculated, with considerable scientific caution and ongoing debate, that a gamma-ray burst occurring within our galaxy at some point in the deep past might have contributed to one of Earth's prehistoric mass extinction events, a hypothesis that remains genuinely unproven and actively studied rather than established fact. So when astronomers looked back at that 1998 discovery of WR-104 and recalled that the clean, nearly circular shape of its spiral strongly suggested the system was being viewed almost exactly pole-on, a quiet, uneasy thought began to take shape. If the spiral nebula appeared so close to circular because we were looking directly down the rotational axis of the binary system, and if the Wolf-Rayet star at the center of that system was destined to explode as a supernova within the next few 100,000 years, and if that star happened to be spinning fast enough at the moment of collapse to produce a long-duration gamma-ray burst, then the geometry of the situation meant that any resulting beam of high-energy radiation might, at least in principle, be aimed almost directly toward our solar system. This idea first reached the wider public in 2008, when the same research team responsible for the original discovery, having gathered an additional decade of follow-up observations at Keck, published an expanded study in the Astrophysical Journal, presenting a sequence of 11 separate, sharp images that traced the spiral's rotation across a full orbital cycle, allowing them to assemble what amounted to a genuine time-lapse movie of the pinwheel slowly turning, like a jewel keeping precise time in a quiet, distant clock. Early estimates derived from these observations suggested the rotational axis of the system might be oriented within somewhere between 0 and 16 degrees of a direct line toward Earth, a remarkably small angle on a cosmic scale, close enough that the possibility, however statistically unlikely in terms of timing and beam width, could not be entirely dismissed out of hand. The press, predictably and somewhat understandably, found this irresistible. WR-104 began appearing in articles and television segments under the nickname the Death Star, a label that, while scientifically imprecise and more than a little sensationalized, was admittedly a memorable piece of writing. Some articles took a careful, measured, scientifically responsible tone, accurately explaining the enormous uncertainties involved, the extremely wide range of timescales over which the eventual supernova might occur, anywhere from tomorrow to several 100,000 years from now, the considerable uncertainty in the actual viewing angle, and the genuine scientific debate over whether the necessary spin conditions for a gamma-ray burst would even be present in this particular system. Other coverage, less careful, leaned harder into the dramatic framing, occasionally implying a far more immediate and far more certain threat than the underlying science actually supported. Even the original research team, to their credit, were notably cautious in how they discussed the implications of their own work. They were careful to point out, even in that 2008 paper, that the degree to which the system's axis truly pointed exactly toward Earth still needed to be firmed up through more precise spectroscopic observation, and that perhaps the single biggest source of uncertainty in the entire scenario was simply that the detailed physics of how, exactly, a massive star's asymmetric supernova explosion and any associated gamma-ray burst actually unfolds remained, and in many ways still remains, a very active and rapidly evolving area of ongoing astrophysical research. So for a number of years, WR-104 sat in this curious cultural limbo, simultaneously a genuinely beautiful, scientifically important prototype object, the very first pinwheel nebula ever directly imaged, and also a minor object of low-grade public anxiety, a star whose name would occasionally surface in articles with headlines designed to make readers a little uneasy before bed. And then, in 2024, an entirely new and considerably more thorough study quietly rewrote a meaningful part of the story, in a way that, if anything, makes WR-104 feel a little less ominous, even as it deepened the genuine scientific mystery surrounding it. Let's slow down here again. Breathe in, slowly, breathe out. We are getting toward the calmer, more settled part of this story now. The new research was led by Grant Hill, an instrument scientist and astronomer at the Keck Observatory, the same facility responsible for the original 1998 discovery, decades earlier. Rather than relying solely on the geometry of the dust spiral, as the earlier studies had largely done, Hill's research approached the system through a completely different observational technique: spectroscopy, the careful analysis of starlight broken down into its individual component wavelengths. Examining the system using data collected with several different instruments at the Keck telescopes across an extraordinary span of time, from 2001 all the way through 2023, more than 2 decades of patient, accumulated observation. By analyzing tiny, periodic shifts in the wavelengths of light coming from the 2 central stars, shifts caused by the Doppler effect as the stars move alternately toward and away from Earth during each orbit, exactly the same fundamental principle used to measure the recession velocity of distant galaxies, or the gentle wobble of a star caused by an orbiting exoplanet. Hill's team was able to directly measure the actual orbital motion and orbital orientation of the 2 central stars themselves, rather than inferring that orientation indirectly from the shape of the dust trail they leave behind. What they found surprised the entire research team, and represents exactly the kind of humbling, unexpected discovery that makes science so genuinely exciting. The orbital plane of the 2 stars, the actual physical plane along which they circle one another, appeared to be tilted at least 30 to 40 degrees away from our line of sight, and possibly tilted by as much as 45 degrees, a considerably steeper angle than the earlier, much smaller estimates derived purely from the apparent roundness of the dust spiral. This finding created what Hill himself described, in comments to the press following the study's publication, as a wonderful new mystery, precisely the kind of moment scientists tend to find more exciting than simple confirmation of what was already expected. As Hill put it, when describing the unexpected nature of the result, the view of the dust spiral from Earth absolutely does look face-on, appearing to spin almost perfectly within the plane of the sky, and it had seemed like a reasonably safe working assumption that the 2 stars themselves were orbiting in alignment with that same visible plane. Instead, the data revealed something genuinely unexpected: a meaningful misalignment between the orientation of the visible dust spiral and the orientation of the actual stellar orbit producing it. This is, scientifically speaking, a genuinely fascinating puzzle, the kind of small but stubborn discrepancy that tends to point toward some additional layer of physics not yet fully accounted for in the existing models. It is possible that the rotational axis of the Wolf-Rayet star itself, the axis around which the star spins on its own axis, separate from the orbital plane of the binary system, is not perfectly aligned with that orbital plane, a phenomenon that does occur in other binary star systems and is sometimes caused by earlier, more chaotic phases in a system's formation history. It is possible there are additional, as yet undetected companions in the system whose gravitational influence is subtly warping the simple picture. The full explanation remains an open and active area of study. But for our purposes tonight, the most important and most immediately reassuring consequence of this discovery is straightforward. If the orbital plane of the 2 central stars, and very likely the rotational axis of the Wolf-Rayet star itself, since the 2 are generally expected to be closely related, is tilted by something in the range of 30 to 45 degrees away from a direct line toward Earth, then any future gamma-ray burst the dying star might eventually produce would almost certainly be beamed off into some other direction entirely, missing our solar system by an enormous margin. As coverage of the 2024 findings summarized it, this new understanding has effectively put earlier fears to rest. The angle involved is simply too large for a narrow, tightly focused gamma-ray beam, which current research suggests likely spans somewhere between roughly 2 and 20 degrees in total angular width, to have any meaningful chance of intersecting Earth. I want you to let that settle for a moment, the way you might let a worry settle and dissolve right before falling asleep. The star that the press once nicknamed the Death Star, the star whose eerie, perfectly circular spiral once seemed to be staring directly down its own throat at us, turns out, according to the most careful and most recent measurements available, to most likely be quietly pointed somewhere else entirely, not at us, just out into the vast, patient indifference of the galaxy, the way almost everything in the universe ultimately is. And even setting the orbital tilt question entirely aside, it is worth remembering something we touched on earlier, and that deserves to be repeated clearly, here, in this calmer moment. The eventual supernova itself is expected to occur, according to current models of Wolf-Rayet stellar evolution, sometime within the next few 100,000 years. That is, by any meaningful human standard, an almost incomprehensibly long stretch of time. The entire span of recorded human civilization, every pyramid ever built, every word ever written, every person who has ever lived, fits comfortably within roughly the last 10,000 years. A few 100,000 years is dozens of times longer than that. Whatever happens to WR104, whenever it happens, it is simply not a concern that needs to occupy any space in your evening, tonight, or for a very, very long time to come. So let's let that worry go, gently, the way you let go of a held breath, and turn our attention instead toward something far more peaceful. The wider family of these strange, spiral-drawing stars, scattered here and there across our galaxy, each one telling a quiet, slightly different version of the same beautiful story. WR104 was the first of its kind ever directly imaged, but it did not stay alone in the catalog for very long. The very same research team, working with the very same Keck interferometry technique, soon turned their attention to other known Wolf-Rayet stars, searching for similar structures, and in 1999, the same year as the original WR104 discovery paper, they found a second example, WR98A, a Wolf-Rayet binary system showing the same unmistakable pinwheel structure, though with some interesting differences. Where WR104 completes an orbit roughly every 240 days, WR98A's two stars take considerably longer, completing a single orbit in roughly 1.5 years. And in an interesting and rather elegant piece of supporting evidence, researchers found that this longer orbital period closely matched a separate, previously known pattern of regular dimming and brightening observed in the star's overall light output, almost certainly caused by the orbiting dust periodically passing in front of, and partially obscuring, the hot inner stars from our particular vantage point on Earth. With two separate, independently confirmed examples now in hand, astronomers were able to confidently establish that pinwheel nebulae represented a genuine, recognized class of astronomical object, rather than some kind of unusual one-off curiosity. In the years since, additional examples have steadily been found, each one adding a slightly different variation to the same underlying theme. WR118, WR112, observed with larger, more extended spiral structures using mid-infrared imaging. WR137 and WR140, both showing similarly elegant spiral patterns, with WR140 in particular, noted by researchers for exhibiting a more visually complex spiral shape than the comparatively clean, simple geometry of the original WR104 prototype. There is even a cluster known as the quintuplet cluster, located remarkably close to the supermassive black hole at the very center of our galaxy, where astronomers found not just one, but several Wolf-Rayet pinwheel structures clustered together in the same dense, extreme stellar environment, an almost unimaginably crowded and violent neighborhood near the galactic core. Perhaps the most striking and most recently studied of these sibling systems is one with a considerably more dramatic name, APEP, named by the discovering research team after the ancient Egyptian serpent deity associated with chaos, a name chosen, quite deliberately, for the way the dust plume's sinuous, twisting form reminded the astronomers who first imaged it of a great winding serpent. First identified through its unusually intense X-ray, infrared, and radio emissions in observations beginning around 2016, APEP turned out to be an even more extreme system than WR104 in several important ways. Rather than a single Wolf-Rayet star paired with one ordinary companion, APEP is a hierarchical triple system containing two separate Wolf-Rayet stars locked together in a close mutual orbit, themselves both being orbited at a greater distance by a third, hot, blue supergiant companion star. The stellar winds in the APEP system are genuinely extraordinary, even by Wolf-Rayet standards, with one component's wind measured at speeds of roughly 12 million kilometers per hour, while the slower-moving dust at the outer edge of the system's enormous nebula trails along at a comparatively gentler, though still extraordinary, 2 million kilometers per hour. Researchers studying the system have concluded that at least one of the central Wolf-Rayet stars must be rotating extremely rapidly, near what is sometimes called critical rotation, the theoretical point at which a star's own outward centrifugal force from spinning nearly balances the inward pull of its surface gravity, a condition believed to be one of the necessary ingredients for a star to eventually produce a long-duration gamma-ray burst when it finally collapses. This makes a PEP, currently located in the southern constellation Norma, somewhere between roughly 8,000 and 15,000 light-years away, depending on which of several published distance estimates you consult, with more recent and refined work generally favoring the larger figure, a particularly significant object to astronomers, identified as the first credible gamma-ray burst progenitor candidate ever discovered within our own Milky Way galaxy. Previously, evidence for the connection between rapidly rotating Wolf-Rayet stars and long gamma-ray bursts had come entirely from observations of vastly more distant galaxies, light-years upon light-years away, making detailed study extremely difficult. Having a genuine, real, physically nearby candidate system, one we can study in actual detail with our own instruments, represents an unusually valuable opportunity, a kind of natural laboratory sitting conveniently within our own cosmic backyard. And yet, even with this more dramatic spin profile, astronomers studying a PEP have been careful to offer the same kind of calm, measured reassurance that the more recent WR-104 study provided. Even a system theoretically capable of producing a gamma-ray burst would still need its narrow, highly directional beam to be aimed with remarkable precision directly at Earth for there to be any meaningful risk at all, and the statistical likelihood of that precise alignment for any given system remains extremely low. As one researcher commented when discussing the discovery, gamma-ray bursters are highly directional, so for a system like this to actually pose any threat, it would not only need to go supernova, it would also need to be pointed in our general direction. Two separate, independent conditions that both need to align, neither of which we have any strong evidence for in a PEP's case. In 2025, the James Webb Space Telescope, with its extraordinary infrared sensitivity, turned its enormous mirror toward APEP, capturing the most detailed images yet obtained of its complex swirling dust structure, revealing intricate layers and textures within the nebula that earlier ground-based observations simply could not resolve. It is a genuinely lovely thing to consider, lying here in the quiet dark tonight, that even as our oldest and most established observatories continue patiently tracking these stars year after year, decade after decade, our newest and most powerful instruments are simultaneously turning toward the very same objects, adding fresh layers of detail to a picture that has been slowly, patiently assembling itself for more than a quarter of a century now. Let's pause again here, take a slow breath, and gently turn our attention toward the deeper, quieter meaning hiding underneath all of this. Why any of it matters, beyond simply being a beautiful and slightly dramatic curiosity tucked away in a forgotten corner of the night sky. When a Wolf-Rayet star like WR-104 eventually does explode as a supernova, whether or not that particular explosion happens to produce a gamma-ray burst, the event itself will be, briefly, one of the most energetic things to occur anywhere within our galaxy in our lifetime, were any of us still here to witness it on the relevant timescale. Wolf-Rayet stars, having already lost the majority of their original mass through their fierce stellar winds, typically explode as a particular category of supernova that astronomers classify as type Ib or type IC, distinguished by a notable absence of hydrogen, and in the case of type IC, also a notable absence of helium, in their observed spectra, a direct reflection of the fact that the star had already shed those outer layers entirely before it ever reached the moment of collapse. In the final moments of a massive star's life, once the core has exhausted every available avenue of nuclear fusion, having worked its way up through hydrogen, then helium, then progressively heavier elements, carbon, neon, oxygen, silicon, eventually producing a core of iron that can no longer release energy through fusion, no matter how it is compressed, the star's internal furnace simply runs out of road. With nothing left to generate the outward pressure needed to resist the star's own crushing gravity, the iron core collapses catastrophically. In a fraction of a second, the outer layers of the star come crashing inward, rebound off the suddenly rigid, ultra-dense core, and the entire star detonates in a supernova explosion, releasing roughly 10 to the 44th joules of energy, an amount so large it defies any comfortable everyday comparison, in a process that simultaneously forges and scatters heavy elements out into the surrounding interstellar medium. Depending on the exact mass of the collapsing core, what remains behind after the explosion is either an extraordinarily dense neutron star, an object so compact that a single teaspoon of its material would weigh roughly as much as a mountain here on Earth, or, for the most massive cores, a black hole, a region where gravity has become so overwhelming that not even light itself can escape its grip. But the explosion itself, however violent and however final for the star, is not simply an ending. It is also, in a very real and important sense, a beginning. The elements forged deep within a massive star over the course of its life, and the additional, even heavier elements forged in the extraordinary heat and pressure of the supernova explosion itself, get flung outward into space, enriching the surrounding interstellar medium, the vast, mostly empty clouds of gas and dust scattered throughout the galaxy. That enriched material, carrying within it carbon, oxygen, nitrogen, iron, and a host of other elements that simple hydrogen and helium alone could never produce, eventually mixes into new molecular clouds, the same kind of clouds that, given enough time and the right gravitational conditions, slowly collapse to form entirely new generations of stars, and, crucially, entirely new planets. This is where the quiet, ongoing dust production of WR-104, even now, decades before its eventual supernova, takes on a meaning that reaches considerably beyond simple visual beauty. The carbon-rich dust steadily spiraling outward from that distant binary system, drifting slowly through interstellar space, is, on a long enough timescale, the same basic kind of raw material that eventually finds its way into new stars and new planetary systems. Every carbon atom in your body, every carbon atom in the air you are breathing right now, in the wood of any tree, in the graphite of any pencil, was originally forged inside the core of some long-vanished star, very possibly a Wolf-Rayet star much like this one, billions of years before our own sun ever formed. We are, in the most literal and scientifically accurate sense available, made from stardust, recycled patiently across unimaginable stretches of cosmic time, passed from one generation of stars to the next, eventually finding its way, against staggering odds, into the particular configuration of atoms currently reading, or listening to, these words. There is something genuinely worth sitting with in that thought, here in the quiet dark, as you drift gently toward sleep. The spiral around WR-104 is not simply a pretty pattern, a curiosity for astronomers to photograph and catalog. It is, in a very real sense, a slow-motion record of star stuff being made, dust assembled atom by atom out of carbon forged in a dying star's core, sent outward into the galaxy, joining the patient, ongoing process that has, across more than 13 billion years of cosmic history, slowly enriched the universe from a place containing almost nothing but hydrogen and helium into a place rich enough in heavier elements to eventually produce rocky planets, oceans, and, eventually, against odds too large to meaningfully calculate, the particular and very temporary arrangement of stardust currently lying here, breathing slowly, listening to this voice, drifting gently toward rest. Before we settle into the final part of this story, let's slow down even further and spend some time with the physics underneath all of this, gently, the way you might trace your finger along a familiar path on a map. There is no need to follow every detail closely. Just let the shape of it wash over you, the way background music does when your mind is already half asleep. Stellar winds are one of those quietly strange phenomena that most people never think about, even though every star, including our own sun, produces one. A stellar wind is simply a continuous outward stream of charged particles, mostly protons and electrons, being driven away from a star's surface and out into space. Around the sun, this is a fairly gentle affair, what astronomers call the solar wind, traveling at speeds of a few hundred kilometers per second. responsible for things like the gentle disturbances that occasionally produce auroras here on Earth, when that stream of particles interacts with our planet's magnetic field. It is, by cosmic standards, a soft breeze. Around a Wolf-Rayet star, the situation is entirely different in scale. The wind is not driven primarily by heat and pressure the way the solar wind is. It is driven by radiation pressure, the simple physical fact that light itself carries momentum, and when an enormous quantity of light passes through gas, it can physically push that gas outward, the way wind pushes a sail. A Wolf-Rayet star is so extraordinarily luminous, often hundreds of thousands of times more luminous than the Sun, that the sheer pressure of its own outpouring light is enough to violently strip material directly off its surface and accelerate it to speeds of 1 to several thousand kilometers per second, fast enough to travel from New York to Los Angeles in under a second. This is not a subtle effect happening quietly in the background. It is, almost literally, a star tearing itself apart in slow motion, year after year, continuously, for the entire span of its brief and dramatic Wolf-Rayet phase. When you place a second hot, massive star nearby, in a tight binary orbit, you create a situation where two of these tremendous winds are aimed, more or less, directly at one another, slamming together somewhere in the space between the two stars. Astronomers refer to the region where this happens as the wind collision zone, sometimes shortened to simply the colliding wind region. It is a place of staggering violence by any ordinary standard, where gas moving at thousands of kilometers per second from one direction meets gas moving at comparable speeds from the opposite direction, and the two flows essentially crash head-on. The kinetic energy of that collision gets converted into heat, producing temperatures that can reach tens of millions of degrees at the immediate shock front, hot enough to strip electrons completely free of their atoms, hot enough to produce strong X-ray emission, which is, in fact, one of the easiest ways astronomers can detect and study these wind collision zones from enormous distances, even when the dust and stars themselves are too faint or too small to resolve directly. And yet, paradoxically, it is precisely in this same violent, searingly hot collision zone that the conditions for solid dust to form actually become possible, a few degrees removed from the immediate shock front itself, in the slightly cooler, denser, shielded pocket of compressed gas that forms downstream of the initial collision. This is one of those lovely, almost poetic ironies that nature seems to produce again and again if you spend enough time looking closely at it. The very same violence that would, on its own, prevent anything delicate or fragile from ever forming, becomes, when properly arranged, exactly the mechanism that allows something delicate to form after all. Two hostile environments, each individually too harsh for dust, meeting at exactly the right angle, at exactly the right density, to create a narrow, temporary protected space where dust can briefly flourish before being swept away into the relative safety of open space. Researchers who have built detailed three-dimensional models of this process using sophisticated radiative transfer simulations capable of tracking how light and heat propagate through a complex asymmetric structure like the WR104 spiral, have found that the geometry of the wind collision zone itself takes the shape of a curved, cone-like surface, sometimes described as resembling the inside of an enormous, gently flared megaphone, wrapped around the less powerful companion star, since the relatively weaker wind from the companion gets pushed backward and shaped by the much stronger, faster wind pouring off the Wolf-Rayet star. The opening angle of this cone-shaped collision zone, the wideness of the megaphone, has been estimated by detailed modeling at somewhere around 40 degrees, a figure that depends sensitively on the relative strength and speed of each star's individual wind, essentially a tug-of-war between two competing pressures, with the shape of the boundary between them settling into whatever configuration balances the forces involved. As the entire binary system rotates, that curved, cone-shaped shock front sweeps around in a circle, like the rotating arm of a lighthouse, except instead of light, what it is sweeping around is a continuously replenished stream of freshly formed dust. The dust does not get created all at once, in a single burst. It is being manufactured constantly, moment by moment, as the orbital motion carries the collision zone through one full circuit roughly every 240 days, each fraction of that orbit contributing its own small arc of fresh material to the ever-lengthening spiral. It is worth dwelling, gently, on just how small the dust grains themselves actually are. In the innermost parts of the spiral, close to where the dust first forms, researchers studying the system have estimated grain sizes of roughly 100 angstroms across, a unit so small it is rarely used outside of atomic scale physics. To put that in perspective, a single human hair is roughly 1 million angstroms in diameter. The dust grains forming in the shock front of WR104 are smaller than most viruses, smaller than the wavelength of visible light itself, which is part of why this dust shows up so clearly in infrared observations rather than ordinary visible light. Tiny particles like this are extremely efficient at absorbing visible and ultraviolet light from the nearby stars, warming up in the process, and then re-radiating that absorbed energy back outward as infrared light, a slightly longer, slightly gentler wavelength. The same basic physical process that makes a dark-colored car feel warm to the touch after sitting in the sun, just happening on a scale and at a temperature suited to deep space rather than a parking lot. Further out from the central stars, as the dust drifts outward across years and then decades, some studies suggest the grains may continue slowly growing, possibly through gentle collisions and gradual accumulation of additional material, with some models allowing for grains as large as roughly 1 micron, still microscopic by any everyday standard, comparable to the size of fine smoke particles, but a meaningful step up from the almost impossibly small grains found in the freshly formed material closer to the center. I find there is something quietly moving in picturing this process unfolding in such complete isolation, light years from anything resembling a witness. No telescope existed anywhere capable of seeing it clearly until the final years of the 20th century, and yet the spiral had already been forming for an unknown, unmeasured stretch of time before that, coil after silent coil, drifting outward into the patient dark, with absolutely no one anywhere to observe it. It is a reminder, gentle and a little humbling, of just how much of the universe goes on quietly, faithfully, entirely unnoticed, simply because the laws of physics do not require an audience in order to keep operating. Let's turn now, slowly, toward a related and equally fascinating thread, the question of orbital mechanics itself, and what it actually means, physically, for two enormous stars to be locked together the way the stars at the heart of WR104 are. When astronomers talk about a binary star system, they are describing two stars that are gravitationally bound to one another, each one orbiting around a shared point in space, called the center of mass, sometimes also referred to as the barycenter, rather than either star simply orbiting around the other in a simple one-sided way. If the two stars were of equal mass, this shared center of mass would sit exactly halfway between them, with each star tracing an identical orbit around that midpoint. In a system like WR104, where the two stars are believed to have somewhat different masses, the center of mass sits closer to the more massive of the two, meaning the heavier star traces a smaller, tighter orbit around that shared point, while the lighter companion sweeps through a wider, more expansive path. Estimating the precise masses, separation, and full three-dimensional orbital geometry of the two central stars in WR104 has proven to be a genuinely difficult observational challenge, precisely because the stars themselves remain too close together and too far away from Earth for any telescope currently in operation to resolve them as two clearly separate points of light. Almost everything astronomers know about this central binary has had to be inferred indirectly, either from subtle shifts in the combined spectral lines of the unresolved system, the spectroscopic method used in the 2024 Grant Hill study, or from the geometry of the dust spiral the orbital motion leaves behind, the method used in the earlier interferometric studies. It is a remarkable testament to how much careful, patient scientific reasoning can extract from indirect evidence, building up a detailed physical picture of a system whose central components have, to this day, never actually been individually seen. Based on the best available estimates, the separation between the two stars in the central binary is thought to be relatively modest by stellar standards, likely only a fraction of the distance between the Earth and the Sun, tucked in close enough that their respective stellar winds inevitably collide almost immediately after leaving each star's surface, rather than having room to expand and weaken first. This close separation is, in fact, essential to the entire pinwheel phenomenon. If the two stars were spread further apart, their winds would have more room to expand and cool before meeting, weakening the collision and likely preventing the dense, compressed conditions needed for dust formation from ever being reached at all. The tight, intimate orbital dance of the two stars is not incidental to the spiral. It is the entire reason the spiral exists in the first place. Let's drift now towards something a little broader, a little more expansive, gently widening our view outward from this single system to the larger population of Wolf-Rayet stars scattered throughout our galaxy, and what studying them collectively has taught astronomers about the late-stage evolution of truly massive stars. Current catalogs list several hundred confirmed Wolf-Rayet stars within the Milky Way, a number that, given the relatively brief duration of the Wolf-Rayet phase itself, likely only a few 100,000 years out of a much longer overall stellar lifetime, suggests there must be a considerably larger total population of massive stars elsewhere in the galaxy currently still progressing through earlier evolutionary stages, on their way toward eventually becoming Wolf-Rayet stars themselves, hidden from us simply because we happen to be observing the galaxy at this particular, narrow slice of cosmic time. Astronomers have found that not all Wolf-Rayet stars follow exactly the same evolutionary pathway, and the details matter considerably for understanding why some of them, like the stars at the heart of WR104 and APEP, end up surrounded by these elegant, persistent dust spirals, while the vast majority of Wolf-Rayet stars show no such structure at all. The traditional, single-star pathway to becoming a Wolf-Rayet star involves a massive star, generally beginning its life with somewhere between roughly 25 and 60 times the mass of the Sun, evolving off the main sequence, passing through an intermediate phase as either a red supergiant or, for the very largest stars, a luminous blue variable, shedding enormous quantities of mass through stellar winds and dramatic eruptive episodes along the way, before finally arriving at the Wolf-Rayet stage, with its outer hydrogen envelope almost entirely stripped away. But research over the past several decades has increasingly emphasized just how significant binary star interactions can be in shaping this evolutionary pathway, sometimes producing Wolf-Rayet stars through an entirely different and considerably faster route. In a close binary system, rather than relying solely on stellar winds to gradually strip away a star's outer envelope, a process called Roche lobe overflow can occur, in which one star, as it expands during its own internal evolution, grows large enough that its outer layers fall under the stronger gravitational pull of its companion star rather than its own, causing material to be physically transferred from one star directly onto the other, sometimes quite rapidly. This process can strip away a star's hydrogen envelope considerably faster and more efficiently than stellar winds alone, producing a Wolf-Rayet star at a younger evolutionary age, and sometimes from a star that began its life with less initial mass than would otherwise be required through the single-star pathway. Because most massive O-type stars are now understood to form in close binary or even multiple star systems in the first place, rather than in isolation, this binary interaction pathway is now believed to play a considerably larger role in producing the Wolf-Rayet population we observe than astronomers once assumed. This matters directly for understanding pinwheel nebulae, because, as we have already discussed at length, the dust-forming wind collision mechanism absolutely requires a close companion star to function at all. A solitary Wolf-Rayet star, however massive, however extreme its own individual stellar wind, simply cannot produce a pinwheel nebula on its own. It needs a partner. And so, in a quiet, almost poetic way, the very same close binary companionship that may have helped strip away a star's outer envelope and accelerate its journey toward becoming a Wolf-Rayet star in the first place, is also precisely the companionship responsible for the beautiful, spiraling dust trail that makes a system like WR104 so visually striking once it arrives at that stage. The relationship between the two stars is not incidental to the story. In a very real sense, it is the entire story, shaping the star's evolution from beginning to end. It's worth pausing here again, breathing slowly, and letting that idea settle. Even among stars, even on the scale of entire suns locked in mutual gravitational embrace, there is something recognizable in the basic shape of this relationship. Two bodies, bound together across an enormous span of time, each one shaped in ways large and small by the simple persistent fact of the other's presence, producing together, through that shared history, something neither one could have ever produced alone. It is, perhaps, a slightly fanciful way to think about astrophysics, but there is no harm in allowing a little gentle wonder into a quiet, late-night story like this one. Let's turn now toward one more piece of this puzzle, a piece that deepens the mystery slightly rather than resolving it, the question of why. When astronomers compare the predicted properties of the WR104 system against the actual observed structure of its dust spiral, certain small but persistent details still do not perfectly line up. The same kind of small lingering discrepancy that, as we mentioned earlier, ultimately led Grant Hill and his colleagues toward their unexpected 2024 finding. One particularly interesting detail involves what astronomers sometimes call a shadowing effect, the theoretical expectation that, as the dusty spiral structure rotates and expands outward, each successive coil of dust ought to occasionally pass directly in front of, and partially block, the light reaching the next coil out, the way the rings of a target might briefly overlap and cast faint shadows on one another if viewed at exactly the right angle. Earlier, less detailed models of the WR104 system had generally assumed this shadowing effect would be a meaningful and detectable feature of the nebula, but the more recent, more sensitive observations carried out using the Sphere and Vizier instruments at the Very Large Telescope found no clear evidence of this expected shadowing at all, a finding that researchers interpreted as suggesting the dusty environment surrounding the star may simply be considerably less massive, less densely packed, than earlier theoretical models had assumed. This kind of small, careful correction, a model slightly adjusted, an assumption slightly walked back, in light of better, more detailed data, is genuinely one of the quieter, less dramatic, but most essential parts of how real science actually works, day to day, study by study. There is rarely a single dramatic moment where a mystery is completely and permanently solved all at once. Instead, there is a slow, patient accumulation of small adjustments, small corrections, each one bringing the overall picture into slightly sharper focus, the way a photograph slowly resolves out of static and noise as a camera gradually adjusts its exposure. WR104 has been under this kind of patient, accumulating scrutiny for more than 25 years now, and the picture, while considerably clearer today than it was in 1998, is still, by the honest admission of the researchers actively working on it, an incomplete one. There is something I find genuinely comforting in that incompleteness, rather than frustrating here in the quiet stillness of the night. It would be easy to imagine that, by now, with telescopes as powerful as the ones currently in operation, every reasonably nearby astronomical object ought to be fully understood, every mystery fully resolved, every question fully answered. But the universe, even in its smaller, more accessible corners, like a single dust-forming binary star 8,000 light-years away, continues to hold back small, genuine surprises, the kind that remind you, gently, that there is still real discovery left to be made, even in places that have already been carefully studied for decades. The universe is, in this sense, endlessly patient with us. It does not mind being looked at again and again, year after year, slowly giving up its secrets, a little at a time, never all at once, never in a hurry. Let's drift now toward the deeper, slower question lying underneath all of this, the one that connects the small, local story of WR104 to something considerably larger, the long, patient chemical history of the universe itself, and the very particular, very improbable place that carbon, the specific element this star's dust is made of, occupies within that history. Carbon is, in many ways, one of the most consequential elements the universe has ever produced. Not because it is especially abundant, though it is indeed fairly common, ranking as roughly the fourth most abundant element in the universe by mass, but because of a peculiar and almost uniquely fortunate set of chemical properties. A carbon atom has exactly 4 available bonding sites in its outer electron shell, which allows it to form an extraordinarily wide and flexible range of stable molecular structures, chains, rings, branching trees of connected atoms, in a way that almost no other element in the periodic table is capable of replicating. This single property is the entire reason an entire branch of chemistry, organic chemistry, exists as a distinct field at all, and it is the entire reason every known form of life, every strand of DNA, every protein, every cell membrane, every single biological structure we have ever discovered, or even theorized about, is built on a carbon framework. But carbon does not exist in the universe by default. In the earliest moments of cosmic history, in the minutes immediately following the Big Bang, the universe produced almost nothing but hydrogen, helium, and only the faintest trace amounts of lithium, the 3 lightest elements in the periodic table. There was, in that earliest universe, no carbon anywhere at all. Every single carbon atom currently in existence, every carbon atom in this script, in the device you are listening on, in your own body, had to be manufactured later, inside the cores of stars, through the specific nuclear process of fusing 3 separate helium nuclei together in rapid succession, a notoriously difficult and finely balanced reaction that physicist Fred Hoyle, studying this exact problem in the 1950s, correctly predicted must rely on a particular, precisely tuned nuclear resonance in order to occur at any meaningful rate at all, a resonance that was indeed later confirmed experimentally. This carbon, once forged deep inside a star's core through this delicate process, remains locked away, inaccessible, useless to the rest of the universe, unless and until something eventually returns it back outward into interstellar space, where it can mix into new gas clouds and eventually become available again for the construction of new stars, new planets, and, on at least one occasion that we know of, new life. There are really only a small handful of mechanisms capable of returning this stellar carbon back out into the wider universe. Slow, gentle stellar winds, of the kind even an ordinary, lower-mass star like the Sun will eventually produce in its final red giant phase, gradually shedding its outer layers back into space. Dramatic, explosive supernovae, violently scattering an entire star's accumulated material outward in a single, catastrophic event. And, sitting somewhere between those two extremes, the powerful, persistent, but non-explosive stellar winds of massive, late-stage stars like Wolf-Rayet stars, continuously peeling away layer after layer of enriched material throughout the final, brief, dramatic chapter of their lives, long before the eventual supernova even occurs. WR104, in this light, is not simply manufacturing a pretty spiral pattern for our telescopes to admire. It is actively participating, right now, in this slow, patient, galaxy-spanning process of chemical enrichment, taking carbon forged deep within its own core through nuclear fusion and steadily, continuously returning it to interstellar space, carried outward inside tiny grains of dust, drifting through the cold vacuum between the stars, available, eventually, decades or centuries or millennia from now, to mix into some future molecular cloud, and perhaps, given enough additional time and enough additional improbable cosmic luck, to one day become part of an entirely new star system with its own entirely new planets, on at least one of which, perhaps, something will eventually arise capable of looking back up into its own night sky and wondering, quietly, where it all came from. It is genuinely worth sitting with the scale of patience required for this entire process, here in the stillness, as your own breathing slows further and your own thoughts begin to loosen and drift. The carbon currently spiraling outward from WR104 will likely take many thousands of years simply to disperse fully into the surrounding interstellar medium. After that, it may sit quietly, mixed into a vast, cold, mostly empty molecular cloud, for millions of years more, waiting, with no urgency at all, for some gravitational disturbance, perhaps the shock wave from a different, unrelated supernova entirely, or simply the slow, patient pull of the cloud's own accumulated gravity, to finally trigger collapse and begin the process of forming new stars. And even then, once a new star and its surrounding disk of planetary material have finally formed, it would still take additional hundreds of millions, perhaps billions of years more, before anything resembling complex chemistry, let alone complex life, could possibly arise on any resulting planet, assuming the right conditions were ever even present at all. The universe, in other words, operates on a timescale so vastly larger than any single human life, so vastly larger even than the entire span of recorded human civilization, that the only honest way to relate to it is with patience, with a kind of calm, unhurried acceptance that most of what is happening out there, right now, tonight, while you lie here listening, is unfolding far too slowly for any of us to ever witness its conclusion. And yet, somehow, that thought, rather than being unsettling, tends to land as something closer to deeply comforting. You do not need to witness the conclusion. You are not required to see how the story ends. You are simply, briefly, gently, part of an extraordinarily long story that was already well underway long before you arrived, and that will continue on, just as patiently, long after you have gone, with absolutely no obligation on your part, beyond simply, quietly, existing for your own small brief portion of it. Let's gently widen the lens one final time before bringing this story to its close, and consider how this single, distant pinwheel fits into the much broader picture of how astronomers currently understand the way massive stars conclude their lives, and what that ending actually involves, mechanically, deep inside a collapsing stellar core. The death of a massive star is, in the most literal sense available, a battle between two opposing forces that have been quietly balanced against one another for the star's entire life. On one side, gravity, the relentless, ever-present pull of the star's own enormous mass, constantly trying to crush the star down into the smallest, densest configuration possible. On the other side, the outward pressure generated by nuclear fusion happening continuously in the star's core, a pressure that, for as long as fusion continues, exactly balances gravity's inward pull, holding the star in a stable, if temporary, equilibrium. For most of a massive star's life, this balance is maintained by fusing hydrogen into helium, the simplest and most efficient fusion reaction available. But hydrogen, even in a star tens of times more massive than the Sun, is a finite resource. Once the hydrogen in the core is exhausted, the star begins fusing helium into carbon and oxygen instead, a reaction that proceeds at a different rate and requires higher core temperatures to sustain. Once helium runs low, the star moves on to fusing carbon, then neon, then oxygen, then silicon, each successive stage proceeding faster than the one before it, the available fuel burning through progressively quicker, as the reactions involved release progressively less energy per reaction, while requiring progressively higher temperatures to even occur. By the time a massive star reaches its silicon burning stage, the final stage available, it is producing iron in its core, and iron is, chemically and nuclearly, a dead end. Fusing iron into anything heavier does not release energy. It actually consumes energy, drawing power away from the very process meant to be holding the star up against its own gravity. The transition through these final fusion stages happens with a startling, almost vertiginous acceleration. Where a star might spend millions of years fusing hydrogen and a comparatively shorter period of perhaps a few 100,000 years fusing helium, the very last stages, the fusion of silicon into iron, can be completed in a matter of mere days, sometimes even less. The star, having spent millions of years in patient, stable equilibrium, races through its final preparations for collapse in what amounts to, on cosmic timescales, the blink of an eye. Once a star's iron core grows large enough, beyond a critical threshold known as the Chandrasekhar limit, roughly 1.5 times the mass of the Sun, there is simply no remaining physical mechanism available to hold the core up against its own crushing gravity. In an instant, the core collapses, falling in on itself at a meaningful fraction of the speed of light. The entire structure that once spanned a region comparable to the size of the Earth, crushing down into a sphere only a few tens of kilometers across in well under a second. This sudden, catastrophic collapse releases an almost incomprehensible burst of energy, most of it carried away not as light, but as neutrinos, ghostly, nearly massless particles that interact so weakly with ordinary matter that the overwhelming majority of them pass straight through the entire remaining outer structure of the collapsing star, and indeed straight through the Earth itself, without ever interacting with a single atom at all. A small fraction of that tremendous collapse energy, however, does get transferred back outward into the star's remaining outer layers, in a complex process involving the collapsing core rebounding against itself and generating an outward propagating shockwave. If that shockwave successfully manages to propagate all the way back out through the entire remaining bulk of the star, rather than stalling partway through and being reabsorbed, the result is the supernova explosion itself, an explosion bright enough, for a period of days to weeks, to briefly outshine the combined light of every other star in its host galaxy, all of it triggered by the collapse of a core only a few tens of kilometers across. It is worth pausing, gently, on just how delicately balanced this entire process actually is, how much of it still depends on extraordinarily fine details not entirely settled by current physics. Researchers running detailed computer simulations of core collapse supernovae have found, somewhat humbling, that getting a simulated shockwave to successfully propagate all the way out through a collapsing star, rather than stalling and failing, turns out to be genuinely difficult to reproduce reliably, requiring careful attention to subtle effects involving neutrino heating, turbulent convection inside the collapsing core, and complex three-dimensional fluid dynamics that simply cannot be captured in simpler, earlier generations of models. This is, even now, a genuinely active and unresolved frontier of astrophysical research, the precise mechanical details of exactly how, physically, a successful supernova explosion actually gets launched. For a star like the one at the heart of WR104, already stripped of its outer hydrogen and helium envelopes by hundreds of thousands of years of relentless stellar wind, the eventual supernova is expected to be of the stripped envelope variety, likely a type Ib or type Ic event, an explosion that, lacking the additional outer layers a less evolved massive star would still possess, tends to evolve and fade somewhat more quickly than other supernova types, while still releasing a comparably enormous total quantity of energy. Current research suggests both the Wolf-Rayet star and its more distant, less evolved companion are each predicted to eventually undergo their own separate core collapse supernovae, given enough additional time, making this not simply a system that will produce one dramatic ending, but, eventually, two, separated by whatever additional span of time the second, more slowly evolving star requires, before it too finally exhausts its own available fuel. Let's stay a while longer in this quiet, unhurried place, because there is one more layer of this story worth wandering through before we finally let it rest, the layer that has to do with how astronomers actually go about studying something so impossibly distant and so impossibly small, and what that effort itself can teach us about patience. When the original team of astronomers set out, back in the 1990s, to study WR104, they were working at the very edge of what was technically possible at the time. The challenge they faced was not simply that the star was far away. 8,000 light-years is, after all, a fixed and unchangeable distance. Nothing to be done about that. The challenge was that the structure they were hoping to see, the dust spiral itself, occupied an angle in the sky so vanishingly small that ordinary telescope imaging, even using the very largest telescopes available on Earth, simply could not resolve it. Earth's own atmosphere, with its constant turbulence, its shifting layers of warm and cool air bending and distorting incoming starlight in unpredictable ways, smears out fine detail long before it ever reaches a telescope's mirror, the same basic effect responsible for the gentle twinkling of stars you might notice on a clear night, lovely to look at with the naked eye, but devastating for anyone trying to capture fine astronomical detail. The technique the team turned to, aperture masking interferometry, is a wonderfully clever workaround for this problem, one that essentially turns a single enormous telescope mirror into something that behaves mathematically like a coordinated array of many smaller telescopes working together. By placing a mask with a carefully designed pattern of small openings over most of the telescope's primary mirror, blocking out the majority of its light-gathering surface, the remaining light passing through the scattered openings can be made to interfere with itself in predictable, mathematically describable ways. By recording that interference pattern and applying techniques originally developed for an entirely different field, radio astronomy, where arrays of widely separated radio dishes are routinely combined to simulate a single, much larger virtual telescope, the team was able to mathematically reconstruct an image with a level of fine detail considerably sharper than the same telescope could achieve through conventional imaging, all while remaining far less vulnerable to the atmospheric blurring that would otherwise have rendered the whole effort hopeless. It is worth appreciating, here in this quiet moment, just how indirect and how clever this entire process actually is. Nobody ever simply pointed a camera at WR104 and snapped a clear photograph the way you might photograph a familiar object nearby. What astronomers actually obtained were complex interference patterns, essentially mathematical fingerprints of the light passing through a carefully masked telescope, which then had to be painstakingly processed using sophisticated computational techniques to reconstruct something resembling a recognizable image. The spiral you might see in a published photograph of WR104 is, in a very real sense, a kind of careful mathematical inference, built up from indirect evidence rather than a simple, direct snapshot. And yet, when multiple independent observations, taken months apart, using these techniques, consistently produced the same underlying structure, rotating in exactly the way the underlying physics predicted it should, the reality of what they had found became undeniable. In the decades since that original 1998 discovery, the tools available to astronomers studying WR104 and its sibling pinwheel systems have continued to improve considerably. The Very Large Telescope in Chile, equipped with instruments like SPHERE, designed originally to help directly image faint exoplanets orbiting nearby stars by suppressing the overwhelming glare of the host star itself. And VISIR, a mid-infrared imager, particularly well-suited to studying cooler, more extended dust structures, allowed researchers in the years following the original discovery to trace the spiral structure out considerably further than the original Keck observations had managed, revealing as many as 5 complete revolutions of the spiral pattern, each one representing roughly 240 days of accumulated dust production, layered outward across what amounts to the past 20 years or so of the system's ongoing activity at the time those particular observations were made. And now, with the James Webb Space Telescope in operation, capable of capturing infrared light with a clarity and sensitivity that earlier instruments simply could not match, partly because it operates from space entirely, free from the atmospheric blurring that ground-based telescopes must always work around. The broader family of pinwheel nebulae, including the related and similarly dramatic APEP system, are being imaged in finer detail than ever before, revealing intricate layering and structure within these dust spirals that earlier generations of astronomers could only partially infer. There is something quietly moving in tracing this progression, decade by decade, instrument by instrument, each new generation of technology adding another careful layer of detail to a picture that began, in 1998, as little more than a faint, 3-frame, jumpy time-lapse sequence, barely sufficient enough to convince anyone that a spiral was really there at all. Science, in its slowest and most honest form, often looks exactly like this. Not a single triumphant breakthrough, but a long, patient accumulation of careful observation, each new study standing on the shoulders of the studies that came before it, slowly, gently, bringing a distant, almost unimaginably small structure into ever sharper focus, until what was once barely visible becomes something we can study in genuine, satisfying detail. Let's turn, gently, toward one more small but meaningful thread in this story, the question of where exactly in our sky WR104 sits, and what kind of neighborhood, astronomically speaking, it calls home. WR-104 lies in the constellation Sagittarius, a part of the sky long associated, in human imagination across many different cultures and many different centuries, with an archer drawing a bow, though most casual stargazers today recognize the brighter portion of this constellation by its more familiar nickname, the teapot, a loose pattern of stars that does genuinely resemble, with only a small amount of imaginative squinting, a teapot complete with a spout, a handle, and a gently curved lid. This part of the sky holds particular significance for astronomers for an entirely separate and even larger reason, because it happens to lie in the general direction of the center of our own galaxy, the dense, crowded, star-filled core of the Milky Way, home to an enormous concentration of stars, gas, dust, and, at its very center, a supermassive black hole with a mass several million times that of our own Sun. Because Sagittarius points us toward this rich, busy galactic core, the region is correspondingly dense with fascinating astronomical objects of every kind, star-forming nebulae, ancient star clusters, and yes, dying, dramatic Wolf-Rayet stars like WR-104. The star itself sits, by cosmic coincidence, almost directly between two considerably more famous and more easily visible nebulae, the Trifid Nebula and the Lagoon Nebula, both popular targets for amateur astronomers and astrophotographers, both considerably brighter and considerably easier to observe than the faint, distant WR-104, which, with an apparent magnitude of only about 13, sits comfortably beyond the reach of the unaided human eye, and indeed beyond the reach of ordinary binoculars or small telescopes entirely. To actually see WR-104, even as a faint point of light, let alone to resolve any detail of its surrounding spiral, requires genuinely serious astronomical equipment, the kind found at major professional observatories rather than in a backyard. There is something fitting, in a quiet way, in the fact that this particular star, capable of producing one of the most visually striking and scientifically significant structures ever directly imaged around any star, sits so unassumingly faint and unremarkable to ordinary observation, tucked away between two far more famous neighbors, in a crowded, star-rich stretch of sky that most casual observers scan right past without a second thought. The universe does not arrange its most interesting objects according to how easy they are to notice. Some of its most remarkable structures sit quietly, patiently, waiting for exactly the right combination of curiosity, technology, and persistence to finally bring them into view. Let's drift, gently, toward one more comparison worth sitting with before we finally let this story rest. A comparison between the patient, repeating spiral of WR-104 and some of the other spiral patterns the universe produces at vastly different scales, because there is something genuinely lovely in noticing how often nature seems to return to this particular shape, again and again, in entirely different contexts, governed by entirely different physical processes. A spiral galaxy, like our own Milky Way, produces its grand, sweeping arms through an entirely different mechanism than the one responsible for the WR-104 pinwheel, involving what astronomers call density waves, slow-moving regions of gravitational compression that sweep through a galaxy's disk of stars and gas, briefly triggering increased star formation as material passes through the compressed region, creating the appearance of bright, organized spiral arms, even though the individual stars within those arms are constantly moving through them, rather than being permanently fixed in place. A hurricane, the kind we discussed only briefly in our earlier broader conversation about rotation, produces its spiral cloud bands through the Coriolis effect, the deflection of moving air caused by the rotation of the Earth beneath it. The shell of a nautilus produces its elegant, gradually widening spiral through a biological growth process, with each new chamber added slightly larger than the last, in a precise mathematical ratio that has fascinated naturalists and mathematicians alike for centuries. And the spiral around WR-104 produces its own particular pattern through yet another mechanism entirely. Simple ballistic outflow from a rotating source, the lawn sprinkler principle, operating not on water and grass, but on stellar wind and interstellar dust, at temperatures and speeds that would instantly vaporize anything resembling a lawn or a sprinkler. Four entirely different physical processes, occurring at four entirely different scales, from the microscopic growth of a mollusk shell to the galaxy-spanning sweep of spiral arms tens of thousands of light-years across, all independently arriving at recognizably similar geometric patterns. There is no deep, hidden, unifying force connecting these examples, no single physical law responsible for all of them at once. It is simply that the spiral, as a basic mathematical shape, turns out to be an unusually common and unusually natural solution wherever you combine steady outward or ongoing growth with some form of consistent rotation, regardless of what, specifically, is doing the rotating, or what, specifically, is moving outward. It is one of those quiet, recurring patterns that nature seems to return to again and again, across wildly different contexts, simply because the underlying mathematics makes it, in some sense, an easy and natural shape to fall into. I find it genuinely soothing to think about, here in this stretch of quiet toward the end of our story together, that the same basic geometric principle producing the gentle, familiar curve of a seashell on some ordinary beach is also, in its own distant, exotic way, producing the elegant, carbon-rich spiral currently winding its way outward from a dying star 8,000 light-years from here. The universe, for all its vastness, for all the genuinely alien strangeness of conditions found at a place like the wind collision zone of a Wolf-Rayet binary, still seems to favor certain familiar, recognizable shapes, again and again, at every scale it touches, as though geometry itself were one of the few truly universal languages, spoken fluently by mollusks and hurricanes and dying stars alike, each one, in its own particular dialect, saying roughly the same thing. Let's allow ourselves one final, slower pass through everything we have gathered tonight, gently weaving it all back together, the way the spiral itself weaves its coils, outward, patient, and unhurried, before we finally let this story rest. Let's bring this all the way back together now, gently, the way you might gather a blanket around yourself before finally closing your eyes. 8,000 light-years away, in a quiet, unremarkable corner of the constellation Sagittarius, two ancient stars, locked together in a tight, eternal orbital embrace, are slowly, patiently coming apart. One of them, a Wolf-Rayet star, has already shed most of its original mass, burning through its remaining fuel at a desperate, accelerated pace, its surface exposed and glowing at temperatures hotter than almost any other class of star known to exist. As its ferocious stellar wind collides with the gentler wind streaming from its companion, the two streams crash together in a narrow, violent shock front, and in that brief, protected pocket of compressed, slightly cooler material, carbon atoms find each other and begin, slowly, to form solid dust, tiny grains no larger than smoke particles, born out of conditions that, anywhere else nearby, would have instantly destroyed them. Carried outward by the relentless pressure of the stellar winds behind it, and swept around in a slow, steady circle by the orbital motion of the two stars producing it, that dust traces an elegant, mathematically precise spiral into the surrounding darkness, coil after identical coil, each one a frozen snapshot of roughly 240 days of the system's quiet, ongoing history, layered outward in time like the rings inside an ancient, slow-growing tree. We found it first in 1998, through careful, patient observation at one of the largest telescopes on Earth, the very first of its kind ever directly imaged. We worried about it, for a while, in the years that followed, when the geometry of that spiral seemed to suggest we might be looking directly down the barrel of a future gamma-ray burst, a worry that, while never entirely irrational given the genuine uncertainties involved at the time, was rooted in incomplete information. And in 2024, more careful, more thorough observation, stretching across more than 2 decades of patient data collection, quietly suggested that the danger we once feared was likely never really pointed our way at all, even as it opened up an entirely new and genuinely fascinating mystery about why the visible dust spiral and the actual stellar orbit do not perfectly align. WR104 will, someday, hundreds of thousands of years from now, almost certainly explode as a supernova, scattering its remaining material, along with all the carbon it has spent these recent millennia quietly spinning outward into the dark, across the surrounding reaches of the galaxy. Some small fraction of that material will eventually drift into new molecular clouds. Some of those clouds will eventually collapse under their own gravity to form new stars. Some of those new stars will very possibly form their own planets. And on some vanishingly small fraction of those planets, if the long, patient, almost unbelievably improbable chain of cosmic events lines up just right, some of that very same carbon might one day become part of something that can look back up at the night sky and wonder, quietly, where it all came from. Let's stay just a little longer with one more idea before we gather everything together, because it touches something genuinely deep about how astronomers think about time, and I think it deserves space here, in the slow, unhurried quiet of this part of the night. When we describe WR104 as sitting roughly 8,000 light-years away, we are also, quietly, describing something about when we are seeing it. Light, however fast it travels, still takes time to cross any distance, and across 8,000 light-years, that travel time becomes genuinely significant. The light currently reaching telescopes here on Earth, carrying the image of that spiral, the information about its current shape, its current rotation, left the system roughly 8,000 years ago. That means, in the most literal and precise sense available, every photograph ever taken of WR104, every careful measurement of its spiral's geometry, every estimate of its orbital period, is a description not of the system as it exists right now, today, but of the system as it existed 8,000 years in the past, around the time human beings were first beginning to settle into early agricultural communities, long before writing, long before cities, long before almost everything we would recognize as recorded history. This is true, to one degree or another, of every single object we observe anywhere in the night sky, but it carries a particular kind of quiet weight when applied to a star already approaching the end of its life. Whatever WR104 actually looks like today, this very moment, as you lie here listening, remains, in a strict and permanent sense, unknowable to us, will remain unknowable to us, for another 8,000 years, the minimum time required for light carrying that information to make the long crossing between that star and our own small, quiet planet. It is entirely possible, statistically unlikely given the timescales involved but not impossible, that the star has already exploded, that the long, patient, slowly spiraling story we have been telling tonight has already reached its dramatic conclusion, the supernova already having occurred sometime in the intervening millennia, with the light and the news of that ending still patiently making its way across the galaxy toward us, simply not yet arrived. There is something genuinely strange and genuinely beautiful in sitting with that thought for a moment. The version of WR104 we study, the version captured in every careful photograph, every painstaking measurement, the version this entire story has been built around, is, in a real sense, a kind of living memory. An image preserved and carried across an enormous span of both space and time. A faithful record of a moment that has already long since passed, the way a very old photograph preserves the face of someone exactly as they appeared on one particular afternoon, even though that person has since grown, changed, aged, and moved through countless additional days the photograph itself knows nothing about. This delay, this built-in lag between what is actually happening somewhere in the universe and what we are currently capable of observing, is one of the quiet, foundational truths of all astronomy, and it applies even to objects considerably closer than WR104. When you look up at the night sky on a clear evening, none of what you are seeing is happening right now, in any meaningful sense. Even the light from the sun itself, our nearest star, takes a little over 8 minutes to reach Earth, meaning you are always, technically, looking at a sun that existed 8 minutes in the past. For the more distant stars scattered across the night sky, that delay stretches into years, decades, centuries, and for the truly distant ones, like WR104, into many thousands of years. The night sky, taken as a whole, is not a snapshot of the universe as it currently exists. It is something closer to a vast, layered collage of moments from many different points in the past, all arriving simultaneously, superimposed on top of one another, each individual point of light carrying its own separate, independent delay, its own separate small fragment of history, quietly delivered to your eyes tonight. I find there is something quietly restful in accepting this, rather than fighting against it. We are never, in astronomy, looking directly at the present moment of anything beyond our immediate surroundings. We are always, in some sense, looking backward, patiently reading messages that were sent long ago, carried faithfully across unimaginable distances by light that never tires, never slows, never loses a single detail of what it carries, until it finally, eventually, after however many thousands or millions of years the journey requires, arrives. And so, tonight, as you drift gently toward sleep, the spiral we have spent so much time with, slowly turning, patiently laying down coil after coil of carbon-rich dust into the dark, is not really a description of right now. It is a quiet letter from 8,000 years ago, finally reaching us, carrying news of a star that was, at that distant point in its own history, still steadily, patiently, doing exactly what it had likely been doing for a very long stretch of time before that, and exactly what, in all likelihood, it is very probably still doing today, even if we will not know that for certain for thousands of years yet to come. There is a particular kind of comfort available in that thought, the same kind of comfort you might find in an old, well-worn letter from someone you love, written long ago, arriving late, but arriving all the same, carrying within it the simple, steady reassurance that, at least at the moment it was written, everything was still unfolding exactly as it should. The universe has been sending us letters like this for as long as there have been eyes anywhere capable of receiving them. Patient, unhurried letters, written in starlight, carrying news from places and times we will never be able to visit directly, but that we are nonetheless permitted, gently, quietly, to read. Let's wander, gently, through one more quiet corner of this story, before we finally let everything settle, because there is a particular kind of pleasure in simply lingering with details, the way you might linger over the last few pages of a good book before finally closing it for the night. When astronomers first began cataloging Wolf-Rayet stars in any systematic way, the naming convention that eventually produced the designation WR104 was not established until 1962, almost a full century after Charles Wolf and Georges Rayet first identified this strange class of stars back in 1867. In that intervening century, astronomers gradually accumulated observations of dozens, then hundreds of stars, sharing the same distinctive broad emission line spectra the two French astronomers had first noticed, scattered across the sky, with no single, unified system for keeping track of them all. It was only with the publication of what astronomers refer to as the fourth catalogue of galactic Wolf-Rayet stars that a clean, consistent numbering scheme finally emerged, simply listing every known Wolf-Rayet star in the Milky Way in order according to its position along the sky's right ascension coordinate, essentially the celestial equivalent of longitude, counting eastward around the sky. WR104, under this scheme, was simply the 104th such star encountered, moving through that ordered list. It is a wonderfully unglamorous, almost bureaucratic origin for the name of a star that would, decades later, briefly capture public imagination under a considerably more dramatic nickname. There is something quietly amusing and a little bit endearing in that contrast, the plain, administrative simplicity of a numbered catalog entry sitting alongside the breathless drama of a tabloid headline, both referring, all along, to the exact same patient, quietly spinning star. Even today, decades after the original catalog was assembled, and even though astronomers have continued discovering additional Wolf-Rayet stars in the years since, requiring the catalog itself to be periodically extended and revised, the Milky Way's known Wolf-Rayet stars are still numbered according to that same original 1962 ordering system, a small, quiet thread of continuity stretching back across more than 60 years of careful, accumulated astronomical record-keeping. WR104 has carried that same simple designation for the entirety of the time astronomers have known it as anything more than an unremarkable, very faint point of light, long before anyone suspected it was hiding. Behind its modest 13th magnitude glow, one of the most visually striking and scientifically significant structures ever found, surrounding any star in the galaxy. There is something worth sitting with, gently, in how ordinary the star appeared for so long before anyone discovered what it was actually doing. For more than a century after its initial cataloging as simply another faint Wolf-Rayet star among many, WR-104 sat quietly in its corner of Sagittarius, unremarkable, unphotographed in any detail, simply another modest entry on a long list, while its spiral, invisible to every instrument available at the time, continued patiently turning, coil after coil, completely unnoticed. It took the specific combination of a sufficiently large telescope, a sufficiently clever imaging technique, and a research team curious enough to point both of those tools at this particular faint star, rather than the countless other faint stars scattered across the same crowded patch of sky, before the truth of what had been quietly happening there finally came into view. This, perhaps more than anything else in this entire story, feels like the right note to end on tonight. So much of what is genuinely remarkable about the universe sits hidden in plain sight, indistinguishable, at first glance, from the merely ordinary, waiting patiently, with no urgency at all, for someone curious enough and patient enough to eventually look a little closer. WR-104 was not always the famous pinwheel star. For most of its long, slow journey through this final, dramatic stage of its life, it was simply another faint star, among the countless other faint stars filling out a crowded catalog, quietly doing something extraordinary, with absolutely no expectation and no need for anyone to ever notice. And perhaps that, gently, is worth carrying with you as you finally drift off tonight. You do not need an audience for the quiet, patient things you do either. The spiral turned for a very long time before anyone was watching. It would have kept turning, just as faithfully, just as patiently, even if nobody ever had. There is a kind of quiet dignity in that, in work and in beauty, that asks nothing of anyone, that simply continues, faithfully, because that is what it is. There is one last small detail worth lingering on, here in these final quiet minutes, because it ties together so much of what we have spent this evening exploring. Every estimate we have discussed tonight, the orbital period of roughly 240 days, the dust velocity of more than 1,000,000 kilometers per hour, the spiral's diameter of more than 200 astronomical units, the orbital tilt of 30 to 45 degrees, the eventual supernova arriving sometime within the next few 100,000 years, every single one of these numbers carries with it a quiet acknowledgement, embedded in the careful, honest language of the scientists who derived them, that science rarely deals in absolute final certainty. Each of these figures comes wrapped in some stated margin of uncertainty, some honest acknowledgement of the limits of current instruments, current models, current understanding. This is not a weakness in how science approaches a star like WR-104. It is, if anything, one of its quiet strengths, the same kind of intellectual honesty this entire channel has always tried to bring to every story we tell here together. The universe is permitted to remain a little bit uncertain. A star 8,000 light-years away, surrounded by a structure too small for any instrument to fully resolve in perfect detail, studied indirectly through interference patterns and subtle spectral shifts, rather than direct, simple observation, is always going to carry some residual uncertainty in exactly how its numbers come out. And that is, genuinely, completely fine. The broad shape of the story remains solid, supported across more than 25 years of independent observation by multiple research teams, using multiple different instruments and multiple different techniques, all converging on a recognizably consistent picture, even as the finer details continue to be gently refined, year after year, study after study. Perhaps that, more than any single fact about Wolf-Rayet stars or colliding winds or carbon dust, is the gentlest and most useful thing to carry with you as you finally drift off tonight. Certainty is not actually required in order to find something deeply trustworthy, deeply solid, deeply real. The broad shape of this story, 2 stars, a violent collision of stellar winds, a slow and patient spiral of carbon drifting outward into the dark. an eventual, distant ending, followed by an even more distant, even more patient new beginning, somewhere else entirely, holds together beautifully, even while countless small, specific details continue to be quietly adjusted, refined, and gently corrected, the way they always are, in every corner of careful, honest science. Let that be enough for tonight. Let the broad, gentle shape of the story carry you the rest of the way, without needing every last detail pinned down perfectly before you allow yourself to rest. Take one more slow breath with me before we close this out completely. In through the nose, gently, and out through the mouth, slower than the breath before it. Let your jaw soften. Let your hands, wherever they are resting right now, go fully heavy and still. There is nothing left to think through, nothing left to solve, nothing left to remember. The spiral will keep turning, whether you are awake to think about it or not, and that, more than anything else tonight, is the quiet permission this story wants to leave you with. You can let go now. The carbon will drift outward at its own unhurried pace, the stars will keep their own ancient orbit, and none of it requires anything further from you tonight except rest. 8,000 years, 240 days, 200 astronomical units, a few 100,000 years more. These numbers will mean nothing to you by morning, and that is exactly as it should be. What matters is only the shape of the thing, the patient, repeating curve of dusk against dark, the quiet, unhurried persistence of two ancient stars, doing what they have always done, asking nothing of you, needing no witness, content simply to keep turning. Whatever brought you here tonight, whatever long day sits behind you, whatever is waiting tomorrow, none of it needs to follow you any further than this sentence. Somewhere out past the edge of everything you can see, a star that does not know your name is quietly drawing the same careful spiral it has been drawing for longer than anyone has been alive to watch, and it will go on drawing it long after this voice has stopped speaking, and long after you have drifted somewhere you will not remember in the morning. Let that be the last thought you carry tonight, soft and slow and entirely unhurried, the simple, steady knowledge that some things in this universe simply keep turning, gently, patiently, without needing anything at all from you. No alarm is set against this story, no task waits at the end of it, no obligation follows you out of it. There is only the slow turn of dust around a dying star, and the slow turn of your own breath, settling now into something close to sleep, matching, if only for these last few minutes, the same unhurried rhythm that has carried that spiral patiently outward for thousands of years already, and will carry it on, just as patiently, long after tonight is over. Just rest now. That is all there is left to do. Good night, very gently, wherever exactly this finds you tonight. Let's gather everything together now, one final time, the way you might gather the last loose threads of a long, winding thought right before sleep finally pulls you under. 8,000 years ago, in a quiet, unremarkable corner of the galaxy, two ancient, massive stars, locked together in a tight gravitational embrace, were doing what they had likely been doing for a very long time already, and what they have very probably continued doing in all the centuries since, even if we will not have confirmation of that for thousands of years yet. One of them, a Wolf-Rayet star, was shedding its outer layers in a desperate, dramatic final act, its surface exposed and blazing at temperatures hotter than almost any other class of star known, where its ferocious wind collided with the gentler wind of its companion, carbon condensed, briefly, into solid grains of dust, smaller than viruses, smaller than the wavelength of visible light, before being swept outward by the pressure of the wind behind them, carried in a slow, patient circle by the steady rotation of the two stars producing them, tracing, coil after identical coil, one of the most elegant and most carefully studied geometric patterns ever discovered anywhere in the night sky. We found it, eventually, in 1998, after centuries of human beings staring up at this same patch of sky, without ever knowing it was there, hidden behind a faint, unremarkable point of light, too small and too dim for any but the most carefully engineered instruments to resolve. We worried about it, for a while, when its geometry seemed to hint at a future we would rather not imagine, a narrow beam of high-energy radiation possibly, someday, aimed in our direction. And we have since, through patient, careful, decades-long observation, found good reason to believe that worry was likely never warranted in the first place, even as new mysteries continue quietly opening up in its place, the kind of mysteries that, rather than being unsettling, are simply part of what it means to keep looking closely at something for long enough. WR-104 will, someday, hundreds of thousands of years from now, by our current understanding, almost certainly explode, scattering its remaining material, and the long, patient harvest of carbon it has spent these recent millennia quietly spinning outward into the dark, across the surrounding reaches of the galaxy, joining the slow, ongoing, patient process that has, across more than 13 billion years, gradually enriched an early universe containing almost nothing but hydrogen and helium into a universe rich enough in heavier elements to eventually produce rocky planets, oceans, and, against odds too vast to meaningfully calculate, the particular and entirely temporary arrangement of stardust currently lying here tonight, breathing slowly, listening to this voice, drifting gently, finally, toward rest. That is the story this particular spiral has been quietly writing, coil by coil, patiently, for longer than recorded human history, and will very likely continue writing just as patiently, long after we are gone, long after anyone remains to watch it turn. Wherever you are right now, whatever night this finds you in, I hope this brought you a little bit of calm. If it did, let me know down in the comments where in the world you are watching from, and what time it is there. I always love picturing the different corners of the world this reaches. And if you'd like more of these quiet, calm, science-grounded stories to drift off to, consider subscribing, so the next one finds you too. Sleep well. Let the spiral keep turning, slowly, patiently, 8,000 light years away, while you finally let yourself rest.